So I'm happy to introduce our next speaker, who's Gilles Delansnay from UMons, that is speaking to us about real-time path planning using Zonotopic extensions to rapidly exploring random trees. So I leave you the stage.
Thank you. So hi everyone. So I'm Gilles Delansnay. I'm a mechatronics engineer. I did my studies in University of Mons, and now I'm a PhD student at the System Estimation Control and Optimization Lab with Prof. Van der Alain as advisors. So I will rapidly present myself and what I'm doing in my PhD. I will introduce a bit the subject and the context. I will present you the two main concepts I will use today and speak about today, notably Zonotope, which is the main theme of my thesis, and how I implement that in everything else. We will show a path planning method that is called rapid random explored trees, and how we can merge both tools together and see how it performs in simulation. So I already told you who I am, and my thesis is based on the robust control of drone application. And in this thematic, I'm focused on developing Zonotopic framework, and in order to extend, for instance, MPCs, controllers, more high-level controllers, partitioning and multi-agent system with using Zonotopes. And so when working on drones, there are already many things that are done with drones in the last decade. They have seen a large development because of the versatility in application and possibilities, especially the ability to go easily into any place, I would say, with all their degrees of freedoms. And those drones, of course, we know how to control them. We also are able to manage the uncertainties and disturbance in the system. But from a more higher perspective, there is always some drawbacks in the control methods. I would say is that we always need to somehow define an objective. And this objective is often some reference to track a given point in space to go to. And as we evolve in systems such as drones, we want to have more autonomous systems that are able to go into direction and move into environment without giving them a particular point in space, at least not by a specific user such as us. And we would like to somehow make them being able to autonomously move in the space and find their way into a finite goal that we might set, but not giving it every key point towards these goals. Additionally, we want also to look at how we can handle collision avoidance, because in those specific systems, it's a huge constraint when you are using drones. It's really important to avoid collision for all the causality it can generate. It can harm humans and materials as well. And we will see how we can include the Zonotopes that I will present just after into this. So the main concern I'm working with are Zonotopes. Zonotopes is a set representation. It represents convex shapes, more specifically polytopes. So polytopes are some convex shapes with a straight line and points. And those Zonotopes exist, of course, from long ago, and they can be defined using their vertices, their edges. They can also be defined by using a half-space representation with linear constraints. But more recently, a bit more than 10 years ago, a new definition has emerged, which is a generator-based definition, which is this one right here. And this new definition enabled a lot of algorithmic improvement in the research, especially in what we call reachability analysis, because we could develop some linear algebra for the zonotopes, and we could use them in mathematical operation directly. Another advantage of zonotopes with this definition is that they scale well with the dimensionality of the system. And so, what is exactly a zonotope, and what is this new definition we have? It's kind of simple, because you have a first element that is this C that is defined as the center of the set. Okay, it's a point in space, so you define your space dimension and you define a point, and then you simply define a matrix with a number of generators. So those are simply vectors that give direction into the space, and the zonotope is simply the linear combination of this center and those generators. So to make it more easy to understand, here's some illustration. So we have a 2D space on the screen, and the first thing we define is the center C. So it's just a point in the space that we can define. And to build the zonotope, we will define multiple vectors that are called generators. And for instance, on the left, you have a first zonotope that is construct using only one generator. So you have this vector that is defined that goes into some direction. And the zonotope is built by the linear combination of the centers and this zonotope in both the positive direction of the vectors and the negative direction of the vector. And as you build zonotopes, you can add as many generators as you want. For instance, in the second case, we have a zonotope with 2 generators. And what we have is that we added, in fact, from the first one, a second generator that is horizontal. And you see that if you take this first one and you shift it along the second generators, it creates you these shapes, okay, these 2D shapes, which is convex shapes, a polytope. And when you define zonotop, you can add as many generators as you want. For instance, you could add, again, vertical generators, and so you are not limited to the size of the space, but you can have infinitely number of generators. And additionally, to those generators, what you can do is add linear constraints to the generators, which allows you to reduce somewhat the space that the zonotopes is representing. Giving you, for instance, these shapes, it allows to go a bit further than zonotopes. It's what we call constraint zonotopes, and it allows to represent any convex polytopes, because in the case of zonotopes, we are limited to a symmetric representation. So what you have to understand is just zonotopes are a set-based representation. It's convex 2D shapes, and it's kind of intuitive representation with one center and a number of generators. The advantages is that you can represent any convex shape, in fact, with zonotope. Just by defining an error, you can always add a number of generators to go below this defined error. Okay, and so how can we use those zonotopes in path planning? I want to discuss a bit on the planning problems and see how we can merge this with zonotopes. In the work we are doing, we are working with what we call rapid exploring random trees. So those trees are sampling methods in which, where you have an environment that is defined with obstacles, you will randomly sample the space with points. And from those points, you will build a tree, and the tree is slowly exploring the environment. And so it's cover more and more the free space available, and from the tree it creates a path that the vehicle can follow in order to reach a goal that we set. And those trees are kind of nice because they are really easy to implement. It's just using random sample and some basic principle, and it's kind of widely used in robotics. So I will give you some illustration of how those tree works. So imagine that you have a starting point in 2D that is right here, and you have an obstacle in the way. And you are trying to reach a specific goal that is given, okay? For us, of course, it's easy to build a path when we look at it, but for the autonomous vehicle, it's not that obvious. And how can we do? The idea is to randomly sample the space. For instance, we sample a point here that is a sample point. The first thing that we do is that we check if this sample is colliding with any obstacle in the environment. In this case, in not the case. When it's colliding, simply we reject the sampling and we sample another point. Then you can link this point to the actual tree. At the first step, of course, the tree is just the first node that is the starting point. And what we do is that we move this sample point closer to the trees, and it creates what we call a new point. And these operations aims at building a point that are actually close to what we are actually exploring, and not building points that are too far away from the trees. And this can be specified by some parameter, the step size parameters. And this build the first branch of the tree with the second node. And this operation is repeated as many times as it needs in order to reach the goal. So at some point, we will continue to build the tree, and at some point, we will achieve to be close enough to the goal, and it will create us a path that is collision-free toward the goal without setting manually the intermediate points to go to these goals. And so here you have a second example. When the tree is built, you have a new sample. You link this point to the closest node in the tree. In this case, it's the second node that we create. And then we bring back the sample towards the tree. And you can do that again and again. One major problem when you see this is, of course, the optimality of the path or its length. Due to random sampling, of course, the path may be kind of arbitrary to reach the goals, and it's not optimized. And your vehicle, we may take a large path or something that is not going straight forward to the goals. This is because the method is not converging to the optimal path. And in order to achieve this convergence, there is a subtotal feature that is added in the RTT star algorithm. And in this algorithm, there is an additional step that is done when you add nodes to the tree. Once you add a node to the tree, you can choose a part of the tree and say, okay, we will look if for every node that we create, we actually take the tree is actually taking the shortest path to go to each node or not. And so we can compute this by a metric. Typically is the Euclidean norm to go from node to node. And if nodes are not the shortest path to go from one to each others, the rewiring operation aims to build new paths within the nodes that are already defined to find the shortest path. And this way, it's possible to show that the path not only will go towards the goal, but that the path that we are creating, the more sample we take, we are converging toward the optimal path. And so now we have seen that eye planning system, we have seen Zonotopes, how we can merge the two. The thing is that in eye planning system, there is still a problem of obstacle representation, because often obstacle will be represented specifically with their shape. For example, we will use circles and represent them with their equation. We will take squares that will represent with some vertices, and so on. And we do not have a single tool to represent the obstacle. We can make ellipsoid in some case, but ellipsoid are kinda conservative. And so the first idea is, in fact, to formalize all this planning and all this environment using the zonotopes, as they can represent bounded volumes in any dimension. And that's the first idea. The second idea is to not only explore point. When we are using the actual algorithm, we sample a single point and build lines between the nodes in the tree. The idea here will be not to sample points, but to sample whole regions, and those whole regions will be represented by zonotopes. And when we do that, we allow for checking not just a single point in a space or checking for a collision into a single line, but an entire region, and we can cover more space, available space in the environment. And so the goal will be to build this node, but you can think it of giving it some thickness to the line that we have. Not only just building branches that gets longer and longer, but also giving thickness to the tree. And this can be done because Zonotopes have many operations are available in the set theory. You can do the Minkowski sum, so it means you can take two zonotopes and make the sum. You can multiply zonotopes by a matrix. You can compute the intersection of two zonotopes, and you can do some collision checking via linear programming. So it's kind of easy to do. And this will allow us to create some kind of corridors in which we could even optimize even better path if needed. So the principle is the same as without using Zonotope. We simply, instead of sampling simple points, we will sample region. And so the idea is directly to define a Zonotope with generators where the generators can be parameters that we fix. It fixes the size of the sampling region we take. And then, thanks to Zonotopic algebra, we can use what is called the convex hull to extend some lines between the initial region that is around the start point and the new node that is created. So the convex hull, you see, is like an extension of the line that we create between 2 points. Here we create a big zonotopes that contains the two initial constants, and it makes a link between the two with thickness. And so as you parcour the tree, you see that you are the space, you are not just building a tree with lines, but you are giving it thickness, and you explore more and more the space. And so now I will show you some simulation results that we did. In those simulations, we have multiple things. We use a variant of RTT because in those algorithms there are many variants to optimize a bit more the algorithm. You have, for instance, a batch RTT, you have informed RTT, and so on with different assumptions. And in this case, we took a real-time approach because we wanted to apply it on a real-time vehicle. So the real-time approach is simply considering the vehicle is already moving along the tree, even if the final path is not found yet. And so on those graphs, you have in green the starting point. In yellow, you have the goal point. And in red, you have some obstacles that are defined by Zonotopes directly. So we give them, typically those are squares, so you give them centers, and you give them two generators, one vertical and one horizontal generators, and it creates you a square. And what happens is that, of course, the blue point is a vehicle that is already moving along the tree, but you don't have to focus on that. And we are able so to explore the space as time grows, the tree grows, and as the tree grows, a path is going towards the goal and until it reaches the goal. Once you reach the goal, there are multiple approaches that allow either to refine even more optimally the path towards the goals, but you can also continue the exploration of the whole space depending on what you want to do. And in this representation, what we have to understand is that the tree is not just line, okay? It's not just line and we make thickness for the representation in 2D. No, those thick lines are the real free space that the tree found, okay? And what you can do is that you can play with what we call the sampling region and the thickness of the tree, and you can begin to explore the space with thicker branch. And when you play with those parameters, you see that you are able to explore more and more the space just by adjusting the thickness, and you don't need to sample as many points as you would need if you didn't use Zonotope, because if you want to explore the whole environment just with points and lines, of course you need an infinite number of points and lines. And in the case of Zonotopes, with just few points, few nodes that you identify, you can sample the whole region, and it allows you to create a map of the free environment in which you can move and explore. And in simulation, we did more complex results where we have a maze-like system, and we may have even a dynamic obstacle in purple. And we show that it's possible to converge toward the goal. But of course, when you see this, there is a clear limitation that appears that concern narrow passage. Because, for instance, if you take a parameterization of the thickness of the tree that is too big, it won't be possible to go through a narrow passage, and your tree and the space you explore will be stuck and cannot pass. So it's important to understand what is the environment, and that the thickness you want to give to the tree is really related to the environment you are exploring. And so these methods really allow to explore the system quite rapidly, and it allows really to cover the whole space thanks to this thickness that we add. Of course, it had some parameter, and parameter tuning needs to be done depending on the environment, and this might be one way of improving the algorithm. And so, thanks to Zonotopes, you are able to have a single representation for obstacles. We can use them directly into the tree to represent the space and explore better the space. There are many operations available which are fast to make the sum of Zonotope, the convex hull. It's a closed algebraic operation. You can make a collision checking very easily with linear programming. And then those paths that you create may not be as optimal because of the thickness you create. So you have some loss of optimality. But if you create big corridors and you explore the space with thick line, you can create huge corridors in which you know that the whole space is free. And so then, if you want, you can use optimization approach to find an even better path within these corridors. And that's it. Thank you for your attention. And if any question, you're welcome.
We have time for one fast question because having three speakers, we have to try to be a little bit faster. Is there one fast question. Michel?
Okay, thank you for the nice talk. I was just wondering when you are taking the, if I understand well, you are taking the convex hull of few successive zonotopes.
Yeah.
And so isn't there a risk that by taking this convex hull, you hit some of your obstacle, or you have to check each time?
So the idea,
you intersect the obstacles for the whole pass?
Yeah, so the idea is to check the intersection between the convex hull and the obstacles. So when you sample the space, the first thing you do is you identify the best node, you create the convex hull, and only then you make the checking, because the point to sample is within the convex hull. So you can directly check the collision with the whole convex hull. And it doesn't change much the linear programming, because you just, when you do the convex hull, you are just adding some generators to the zonotopes. So you have a new zonotope with additional generators, and you can just make the linear programming for the collision checking.
Okay, but so you could reject some samples due to the conservatism introduced by taking the convex hull?
Yeah, of course. The idea was to expand when you take the convex hull, you somewhat expand linearly the sampling region from the node toward the new point we are creating. So of course, we could have case where if we just created a line, we would not have intersection, but if we create a convex hull, we create an intersection because of the additional space we take. And that's one limitation of the algorithm, is that when you are close to obstacles, you may need, in fact, refine the sampling region. In the algorithm, we choose to keep a constant value for the sampling parameters. But I think that one way to improve it is, okay, to say if the closer we are to obstacle, maybe we could adjust the sampling parameters to get smaller region, and so to be able to avoid this phenomena that may appear when you are really close to obstacles.
Okay, thank you.
So with this, another applause to thank Gilles.
Thank you.
Thank you for coming.